Okay, so let's start with a small chapter, chapter 8 as per GARP. It's called model evaluation. It's a very small chapter, hence may not take very long. So, model evaluation means that how do we validate if the model is good or bad. So, actually, the entire chapter is going to talk about how do we empirically measure the goodness of model. So that's the entire chapter that we are going to cover today in next half an hour or so. So since we understand there are two kinds of models, I mean there are many models, but we generally talk about regression and classification. So since the models are very different, this is more on the continuous variables, and so whatever you predict has a continuous range of values. And in classification, generally it's a, whether it is a binary classification or it's a multi-class classification, your prediction or your output is more discrete. So your evaluation of models for regression and classification is slightly different. So let's start with regression models. So now, as you understand, in case of regression models, your output is discrete. Let's suppose you are getting some output as yi. So you have a set of variables, and then you find a function of those variables, so on and so forth, and then you predict what is the output of that variable. Now and then when you have some of your, let's suppose you want to run this on a test data set, you will also have the actual values of yi. So the first metric that we use is called as MSE. It's called mean squared error. So what we do is we subtract this from the actual value, we do the square of it, we add all the values which are in the test set, and we divide it by n. So that gives you the mean squared error. It's a good metric. You can measure most of these things. Most of it, it's a good metric. I mean, there is nothing wrong with this, because anyway you are doing the square. So whatever deviations you have on the positive or negative side, that are anyway going to get nullified. The problem with this error is, let's suppose you are trying to predict the say you are trying to predict the age of an individual. So and let's suppose your mean squared error is, say, let's suppose 50, and you cannot physically interpret what does 50 mean, because your values, let's suppose you are trying to predict the age of people, so 50 may look very big number, that your predicted age is say plus minus 50 of your actuals, which is actually not the case, since it is a squared thing. So things become difficult to interpret. So in that case, what we do is we do root mean square error. Okay, so the metric of root mean square error means that we are trying to put the or the final metric in the same scale where your actual values are. So it is nothing but your under the root of mean squared error. So which is your 1 upon n yi minus yi hat squared under the root. So in this particular case, if you do under the root of 50, it will become 7 point something. So you'll say, okay, my root mean square error is 7, which is fine, because now it means that your predicted values are going to be in the range of plus minus 7 or so on and so forth. So that's called the root mean squared error. The problem with root mean squared error could be that, let's suppose you are trying to model the salary of a person based on, say, parameters like experience, skill, and so on and so forth. Let's suppose you find out the salary of the person is 10,000 and the actual salary is 12,000. Okay, or you find out the salary of the person is, let's suppose, 95,000 and it is actually 125,000. Okay, now in this particular case, or just to make it look a little more easy, let me say this is 100,000 and this is 120,000. Okay, so now in this case your difference is 2,000. In this case also the difference is 20,000. 10,000, 20,000. Okay, or if it is 102,000 or so. So if you're, so in this case it is this, if let's suppose there is 100,000 and this is 102,000, the difference is 2,000. Okay, so you are trying to get the values, the difference of values irrespective of what is the base value. So to cope with these kind of situations, we do root mean square average, or we do we do the root mean square with respect to I'll say we say root mean square error relative, and in this case you don't just subtract, you also divide by yi and then you square it off and then you do this sigma. So you are doing this in a kind of a relative ranking. Okay, so you are just trying to proportionate it, or make sure that this and this and this and this are not considered similar. So that's why you divide with the base value. Okay, then another the problem with some of these squared errors is that it is very, very prone to outliers. Okay, so till the time things are in the range, you say, oh, plus minus 7, it is okay. But if there is one or two odd values, and suppose this is your predicted, there is one value that is here. Okay, so if there is an outlier, this entire thing gets very nasty, because one outlier, and because it's going to be squared, so the outliers become very, very large and your overall metric goes for a toss. So to compensate for those kinds of issues, we also find mean average error. Okay, in this case, instead of squaring off this, we just try to find out the mod values and then you divide them by n. Okay, so that's the mean average error, and very, very similar to what we did here, there is something called as MAPE, which is called as mean average percentage error. Okay, so this is mean average percentage error. The same thing which I was telling you here, to compensate for the fluctuation with respect to the actual value of that particular row or yi, we divide this by yi and then we take the mod and then we divide it by n. Okay, so this is called MAPE. So these are some of the matrices that we can use in case of regression. So very simple to understand, and very easy to calculate and compute. So if you are given a set of values in exam, you may be asked to find out one of them. You can do some exercises, and it is very say elementary school level mathematics. So that takes care of regression. Now let's talk about classification. Classification is a little more tricky because in this case you don't have continuous values and you cannot just subtract them, square them and find the average. So while the methods are independent of the number of classes, but most of the explanation that I would do, and even GARP or any book also does, is going to be on the binary classification. So we are saying that there are only two classes, positive class and negative class, and then we try to do all these matrices. If you think, or if you in a scenario where there are more than two classes, let's suppose you have class A, B and C, it is very easy to take these matrices to multiple class by saying that, you know, if A is positive and B, C is negative, and then you can say, okay, in the other case B is positive and AC is negative. So it can eventually go down to binary classification itself. So one of the fundamental metrics, or one of the fundamental thing that we compute in case of classification is, you know, we create this kind of a metric. Let's suppose this is your actual classes. Okay, and these are your predicted values. Okay, let me also make a small thing here like this. I'm not good in drawing, but let it be. I don't know if I can remove this. No. Okay, so let's say this is positive, this is negative, and similarly this is positive and this is negative. So this means that the predicted values, I'm predicting this to be positive, I'm predicting this to be negative, and these are the actual value. It is actually positive and it is actually negative. So for all the and this is my model prediction, and this is my actual, you know, labeled values. So if I'm predicting a value as positive and it is actually also a positive, which is the good thing, this thing is called as true positive. So true positive means that it is actually positive, you know, and I am also marking this as positive. Now let's suppose it is actually negative, but I am marking this as positive. So the model is saying it is positive, but actually it is a negative. So it is called as false positive, you know, because though I'm saying it is positive, but that's a false claim. So it's called as false positive. If it is actually positive and I'm calling it as negative, it's called as false negative. And if it is a negative and it is also actually a negative, it is called as true negative. This particular table is called confusion matrix, and this is very important to understand very thoroughly. You can pause, you can repeat, you can look out for more videos, but you need to understand this kind of a metric very nicely, so that you understand what is true positive, what is false positive, false negative and true negative. Now whatever matrices we are going to talk is going to be some or the other combinations of this thing only. Okay, let's suppose we are talking about a model which predicts whether it is cancer or it is not a cancer. Okay, so So this is my prediction and this is my actual. Let's suppose it is saying that it is marking 100 cases as cancer, which are also actually cancerous. Now it is also saying that 50 more cases as cancers, which are actually not cancers. But it is putting some, say, value of 5 here. And then let's suppose, so it is 105 is your total of these things. So this also needs to be, so this is my predicted values. Okay, and these are my actual values. So actually, and let's suppose these are my, this is my, again 50. Okay, so in this case, what is most important is this value. Okay, because if I claim anything as non-cancerous and it is actually cancerous, this can create a lot of problem. See, it is okay for me to mark somebody as cancerous. The person may be cancerous, may have a cancer or not cancer. It is a kind of a false positive. So the impact of false positive, there is an impact of false positive. Ideally, these both values needs to be minimized and these both values needs to be maximized. Okay, so these to be maximized and these two to be minimized. But if I have to pick one of these two, what is more important? This value is very, very important. Okay, I cannot predict a value as negative or non-cancerous when it is actually a cancerous claim. So it is kind of a based on scenario to scenario. You need to understand what is it that is most important to you. Now there are some metrics that we use. One is called precision. Now precision generally also in your day-to-day language also means how good you are with respect to what you do. So precision is nothing but true positive upon true positive plus false positive. Okay, so what it means is that out of all the cases that you have said as positive, what is the ratio of this with respect to the claims that you are making. Okay, so in this case, when you are saying your positive is 150, out of 150 you actually 100 are the true positive and the remaining 50 you are claiming to be positive, but actually it is not positive. So your value is going to be 100 upon 150. Okay, or 2 upon 3. So your precision is 66% or whatever you want to call it, which means that the quality of positive predictions is 66%. 66% of your positive predictions are actually correct and the remaining 100 minus 66 is actually not correct. Okay, it is good to have a high precision. The second thing is called as recall, which is true positive upon true positive plus false negative. Okay, so what this means is that out of all the positive cases that are there in the true world, okay, so in the true world there are 105 positive cases, 100 that we have actually identified, 5 that we could not identify. Okay, now out of those 105 we are actually able to predict 100. So the recall is going to be 100 upon 105. Okay, which is going to be a good value, maybe 90% or whatever this value comes to be. So this is recall, which is, again, just to repeat, recall tells me out of all the positive cases in your test set or in the real world, how many of them it is able to actually identify. And precision means that out of all the positive cases that it has identified, how many of them are actually positive. Now Garth may ask you that in what scenarios precision needs to be considered, in what cases recall needs to be considered, etc., etc. So that depends upon um, time to time or scenario to scenario. When you cannot afford to make mistakes with respect to marking a value as, say, false negative in case of like cancer diagnosis, etc., recall is more important. And sometimes if you want to even in frauds, etc., recall is very very important. But in cases where you don't want to make a false positive, because of making a marking a value as false positive can give you a very very bad customer experience, and those kind of things, precision is very very important. We also sometimes do something called as we can take the mean of both of these, but instead of taking a regular mean, we take the harmonic mean. So if you remember from your elementary maths, what is harmonic mean? What we do is we take the inverse of precision, we take the inverse of recall, we divide them by 2, and we take the reciprocal. And so it is going to be, see, PR upon PR, and so what is the final value that we get is so if I want to simplify this will become R plus P upon PR divided by 2, and then the inverse, so eventually it becomes 2 PR upon P plus R. Okay, so and this is an harmonic mean where we have taken the precision and recall in same proportion. Okay, so the weightage of precision and recall is same. So you can also say that in my particular case recall is more important, so I'll take 70% of this, so this gets multiplied by 0.7, this gets multiplied by 0.3, and then you can do all this math again. So the harmonic mean is able to give you the mix of precision and recall, and harmonic mean, or it is also called F1 score, is also used in some scenarios. There are a few more terms which I would want to tell you without making you confused. These are some of your rates. So and all these rates are also kind of associated with this confusion matrix only. Let's start with simple true positive rate, okay, TPR. So what this means is true positive rate eventually means that how good it captures the positive cases. Okay, so this is true positive upon true positive plus your false negative. Okay, and if you recall, this is nothing but recall itself. So this says that out of all the positive values that were there, how many have you classified correctly? So it's called a true positive rate. There is one more term that some people use for this is sensitivity. This is very very, some of these terms are very important to know. That's why I am just trying to mark them separately. There is true positive rate, there is also false positive rate. Okay, which is nothing but as false positive upon of course false positive upon true negative plus false positive. Okay, so this is the This is the rate of how good your model is with respect to capturing your negative values. Okay, so false positive are the ones that are indirectly classified as positives divided by actual the true negatives, which it is classifying as negative and it are actually negative, plus the false positive. So that's called the false positive rate. There is one more rate which is called as true negative rate. You can keep this in your notes, because it is going to be very, very important. The GARP is definitely going to ask some of these questions around this. And this true negative rate, the another name for this is specificity. So somebody may say, what is the specificity? Which is nothing but as a true negative rate. So true negative rate, again, it is going to be true negative upon true negative plus false positive. Okay, so this tells me how good is the detection of your true negatives. So true negatives needs to be identified nicely, and true positive also needs to be identified nicely. So there is one very, very important graph which is between these two rates, and which is also very, very important question, not just in GARP, but if we have to take interviews of people and we want to look at their understanding on model evaluation, we always talk about this graph, where what we do is we make a graph around false positive rate and so this is your false positive rate, true positive, false positive rate and your true positive rate. Okay, so we find out this false positive rate, and which is, so that means this is a graph between these two, not this one. So ideally your false positive rate should be minimized and your true positive rate should be maximized. And since this is a rate, this can have values from 0 to 1, and this rate can also have values from 0 to 1. And so what happens, let's suppose we are talking about, so this is kind of a measure in which you try to, let's suppose we are talking about a logistic regression. Okay, now in case of a logistic regression, your output is always a probability, and then you find out some kind of a threshold, and most cases, let's suppose the threshold is 0.5. If the value is above this threshold, you mark that as class 1. If it is below this threshold, you mark that as class 0. But you can have multiple values of this threshold. So in this particular case, what we do, we find out different values of the threshold, and based on the different values of threshold, we find out what is the false positive rate, what is the true positive rate. And so this is a kind of a, this particular graph is called as ROC, receivers operative curve. And if it looks something like this, it is considered good. Okay, because if it happens, if this dotted line means that your model is as good as making a random guess. Okay, so your area under this curve needs to be maximized. So ideal case is that you reach here, which means that your false positive rate is 0 and your true positive rate is 1, but practically that's not possible. So you need to find out models that can give you the maximum value of your area under the curve. So the more is the area, which means that if your curve is happening above this threshold line, it is better than making a random guess. If your model is something like this, then it means that it is better that you do your predictions randomly rather than using a model, because the model is going to give you more versor values for various values of threshold. So this kind of analysis or this kind of model evaluation is good to evaluate a model independent of the value of threshold, because you are trying to use various values of threshold and then trying to model this and then try to find the area under the curve and say, okay, this is my logistic regression, this is my, let's suppose, decision tree, and let's suppose there is one more, which is your neural network. So which one works the best? Maybe neural networks works the best, obviously, and then you pick up this model. So that's the end of this reading. It's a small chapter. Small chapter, but a very, very important chapter. You can do some questions around it. There can be tricky questions, there can be questions related to formulas, what is precision, recall, F1 score, AUC. They can give you different kinds of these curves, which one is better, which one is not so better, and you can intuitively answer it. See you in the next video. We have 2 more readings left for module 2, and then we'll be done with module 2. One is NLP and the other one is Gen AI. So we'll cover this next. Gen AI is very, very evolving field. So I'll still go with what is written in GARP, RAI syllabus, but every other day there are new developments that are happening in Gen AI. I'd still stick to what is there in GARP. NLP is more fundamental natural language processing. So we'll try to finish these 2 readings first and then move on to module 3 and module 4. Thank you.